everyone, and welcome to a special introductory lecture for our environmental change units. For the rest of this semester, we are going to be talking about examples of hydrologic change. We will have a series of guest lectures talking about how anthropogenic change in specific environments, things such as forest harvest, urbanization, land drainage, and climate change, impact land surface hydrology. Before we get into that, I think it is important to review something that we've only hinted at until now, and that is how the land surface energy balance interacts with the land surface water balance. Our learning objectives for this lecture are to review methods of heat transfer and relate this to the land surface energy balance, describe the difference between different radiation terms, and describe the conservation of energy and how this interacts with the land surface water cycle. Methods of heat transfer refer to the mechanisms by which heat moves from hot bodies to cold bodies, and this transfer can actually occur by four different mechanisms: radiation, conduction, convection, and vaporization. Radiation is, of course, how heat gets to us here on the Earth from the sun. Heat transferred as radiation travels as waves, where the wavelength is determined by the temperature of the radiating body. The important distinction is that radiation can travel through the vacuum of space. Otherwise, we couldn't feel the heat of the sun. It doesn't have to have a vacuum, though, so we also experience radiation transfer down here on the Earth's surface, too. Conduction, in contrast, requires direct contact. Heat is transferred from molecule to molecule, so it cannot happen through a vacuum. It is conduction that makes the metal handle of a pan get hot when it has been left over a campfire. Conduction can also happen through air, so that the air in contact with a hot parking lot will warm up. Convection requires the mixing of air or water masses. Here we are showing warm water entering into a cold receiving stream. The stream water will warm up as these two liquids mix together. A convective oven works to cook food faster because it has a blower to circulate warm air around your food. A traditional oven relies on conduction to bring the heat from the heating elements to your food. In the atmosphere, we talk about convection associated with thunderstorms, when air warms by blowing over a hot land surface and then rises and mixes with cooler, moist air. Our final method of heat transfer is not technically a method of heat transfer at all, but more a method of heat consumption or release. Vaporization refers to the heat involved in phase change. This latent heat is the energy consumed to thaw ice or evaporate water, or the energy gained when water freezes. It is considered a latent heat because it cannot be touched or sensed. Each of these methods of heat transfer are happening in the natural environment, and so if we bring them together, we have a statement of the land surface energy balance. The change in heat energy stored in an object, such as the thin layer of soil, dSdt, is equal to the energy transferred by radiation, both shortwave, QSW, and longwave, QLW, plus the energy transferred by conduction and convection, which are together referred to as sensible heat, QH, plus the energy consumed by vaporization, which is called the latent heat flux, QLE. Note that all of these terms, except for the net solar radiation, can be negative, so they may represent either a gain or a loss of energy to the land surface. I'm now going to talk about each of these terms in a little more detail. A theoretical black body is an object that is both a perfect emitter of radiation and a perfect absorber of radiation, with no losses in the system. The energy emitted by these theoretical bodies is called black body radiation, and it can be used as an approximation of the energy emitted by real objects, such as the sun or trees or you and I. All objects emit radiation. The total energy emitted from a black body as radiation is proportional to the temperature of the object to the fourth power. So temperature times temperature times temperature times temperature. The wavelength of the emitted radiation also varies with the temperature. such that hotter objects emit radiation with shorter wavelengths, as shown here in the yellow illustration. This leads us to the difference in the electromagnetic spectrum of solar radiation and the radiation emitted by the Earth and the things on the Earth. Because the Sun is 30 times warmer than the Earth, it emits much more total energy, and that energy is at much shorter wavelengths, from 0 to 2 micrometers. These wavelengths include the visible spectrum that can be seen by the human eye. It also includes the ultraviolet light that causes sunburn, as well as infrared light. In contrast, objects on Earth with a mean annual temperature of 288 degrees Kelvin, or about 15 degrees Celsius, emits radiation between 3 and 27 micrometers. This is why we refer to radiation from the Earth and atmosphere as long-wave radiation, while solar radiation is called shortwave radiation. The QSW and QLW terms in the land surface energy balance usually represent the area under these curves, that is, the total emitted energy, irrespective of wavelength, although in specific applications it may be important to know the total energy between certain wavelengths. In addition, QSW and QLW represent the net radiation incident on a surface. That means it is the difference between what comes in and what goes out. In the case of solar radiation, incoming solar radiation comes from the sun, but some portion of it is reflected off of the surface, as illustrated by the sunlight reflecting off this bright white snow. The net radiation is the difference between the incoming and reflected portions. It is the energy that is available to either be absorbed by an object, like the snowpack, to eventually melt it, or the small amount that may be transmitted through the snow to warm the underlying soil. So once again, net radiation is equal to the incident incoming radiation minus the reflected portion. Albedo refers to the reflectivity of the Earth's surface to solar radiation. So you can see that things like snow and clouds up here have very high albedo, reflecting away most of the incoming solar radiation, while exposed soil has a much lower albedo. Long-wave radiation, in contrast, does not reflect off of the Earth's surface. The longer wavelengths are absorbed. This absorbed energy warms the object, which then starts emitting its own long-wave radiation. So here I'm showing the variable RB, which is the variable that the book uses to refer to long-wave radiation, while I've also used the nomenclature QLW to be consistent with the book's statement of the land surface energy balance. So net long-wave radiation represents the difference between the radiation emitted by the atmosphere. Let's circle that in green here, which travels both towards space, because it's emitted in all directions, as well as back towards the land surface. And then the balance between that and the radiation emitted by the Earth's surface down here. In the evening following a warm day with clear skies, net long However, on cold winter days with a lot of cloud cover, net long-wave radiation may be positive, since the clouds could be warmer than the snow-covered land surface. So the atmosphere emits more radiation than the land surface, and incoming will be greater than outgoing. The remaining two terms of the land surface energy balance are sensible heat and latent heat. Sensible heat represents the heat exchange by conduction that can be felt, such as when the land surface warms up because a warm air mass moves into the area, or if your feet feel cold if you walk barefoot on a cold driveway to get the newspaper on a winter morning. Sensible heat is pulling the heat away from your feet and into the underlying ground. Latent heat, in contrast, is the hidden heat associated with phase change. Excess energy must be available from radiation or sensible heat in order to provide the energy needed for evaporation and snowmelt. This final set of illustrations can help us to think through why the energy balance is important. This image shows a typical distribution of energy fluxes over a moist surface, such as a well-watered grass field during the daytime. Net solar radiation is always positive during the day, so the yellow arrow is showing energy coming to the land surface, the sum of shortwave and longwave radiation. This is energy that can be used both for latent heat, shown in blue, and sensible heat, shown in red. Latent heat is therefore showing that it is taking energy away from the land surface, meaning that evaporation is happening, consuming energy needed for phase change. Sensible heat is also taking energy away from the land surface, both by warming the overlying air and warming the underlying soil. This flux of energy into and out of the soil is a form of sensible heat transfer that is often called ground heat flux. In contrast, at night, solar radiation becomes zero, so the net radiation often becomes negative due to a negative net long-wave radiation. So now the yellow arrow is pointing away from the land surface. As a result of radiation taking energy away from the surface, sensible and latent heat may also reverse their direction. A negative latent heat implies that the energy of phase change is being released, so water vapor is condensing into dew, or snow is refreezing. The final scenario is similar to the first, but now we are looking at a dry surface, such as a parking lot during the day. Since there is no water available to evaporate, latent heat cannot take up any of the excess energy. It's equal to zero. Therefore, all of this energy will be used to warm the underlying asphalt, and then will be transferred to the overlying air as sensible heat. This is why you will feel much warmer standing in the middle of a parking lot on a hot summer day than if you were standing on a grass soccer field. This concludes our introduction to the land surface energy balance. You can explore these terms more using the energy balance Quizlet.